Roadmap for today. We'll start off with the acid-base mystery, then move on to comparing acids and bases. After that, it's testing the unknown, followed by reactions and neutralization, and finally, we'll wrap things up with the power of pH.
All right, let's kick things off with Section 1, the acid-base mystery.
We're going to start by looking at chemical properties, not just as, boring facts to memorize, but as a real-world puzzle we actually need to solve. So, picture this. Someone in your family just ate way too much at dinner and they're suffering from some serious acidity. Which of these remedies would you actually suggest? A glass of lemon juice, some vinegar, or a baking soda solution? Think about the underlying property you're relying on to make that choice. I mean, you definitely wouldn't give them more acid, right? You'd want something to actively nullify that acid. And this perfectly illustrates how these substances interact. You'd go with the baking soda because it acts as a base to basically cancel out the stomach acid. Now, we can actually see these interactions happen visually using things we call indicators. Have you ever noticed how a bright yellow turmeric curry stain on a white shirt suddenly turns reddish-brown when you scrub it with soap? Well, that happens because soap is basic in nature and turmeric is a natural indicator. Then when you wash it out with plenty of water, it magically turns yellow again. So before we move on, here's a question to chew on. Can you think of any other natural indicators hiding in your kitchen?
Moving right along to Section 2, comparing acids and bases.
Now that we know they interact with each other, we really need to formally compare these two heavy hitters of chemistry. Acids, like that lemon juice we talked about earlier, have a very distinct sour taste. If you test them using a natural indicator like blue litmus paper, an acid is going to turn it red. And down on a microscopic chemical level, acids generate hydrogen ions, that's H+ ions, when they're in a solution. Bases, on the flip side, taste bitter. Think back to that baking soda. They do the exact opposite to litmus paper, turning red litmus blue, and chemically they generate hydroxide, or OH- ions.
But here's something super interesting. Indicators aren't always purely visual. We actually have olfactory indicators too, things you smell, like vanilla essence, chopped onion, and clove oil. If you put these into an acidic or a basic media, their actual odor changes. So I want you to put your thinking caps on for a second. Why do you think their smell changes depending on whether they're in an acidic or basic environment? What exactly is happening down at the chemical level to cause that?
All right, time for Section 3, testing the unknown.
Go ahead and grab your imaginary safety goggles, because we're heading straight into the laboratory. How do we safely categorize liquids when we absolutely can't taste or smell them? Well, to get really precise visual clues, we use synthetic indicators. Let's say you have a totally unknown liquid. You drop in a little phenolphthalein, and nothing happens. It stays completely colorless. Boom, you know you've got an acidic solution. But if that liquid suddenly turns a vibrant, bright pink, you've definitely got a base on your hands. Or take methyl orange. It turns red in an acid, but a sunny yellow in a base. It's almost like a secret, color-coded language just for chemistry.
Now here's a classic experiment straight from your textbook that shows us another awesome way to test substances. In this setup, we're reacting solid zinc granules with dilute sulfuric acid. Do you notice those bubbles forming in the tube? What's happening is the metal is actively displacing hydrogen atoms right out of the acid, which forms a salt. Then, we take that evolved gas, pass it through a soap solution, and that's what creates those amazing bubbles you see rising up. Now pay close attention to what happens when you hold a burning candle right up to those soap bubbles. Pop! You get a tiny little explosion. So based on what we literally just discussed about the metal displacing atoms from the acid, I've got another question for the class. Which specific gas is being liberated that makes that highly distinct popping sound with a burning candle? Think about the one thing all acids have in common.
Let's dive into Section 4, Reactions and Neutralization.
Let's shift gears for a minute and look at the chemical formulas that describe what actually happens when these powerful substances collide. A neutralization reaction is simply the reaction between an acid and a base to give a salt and water. So, base plus acid yields salt plus water. Remember our overeating example from the beginning? The basic baking soda and the harsh stomach acid reacted, completely neutralizing each other's effects. They brought immediate relief by producing totally harmless salt and water. So, if mixing an acid and a base neutralizes them both, what do you think happens if we dissolve just an acid all by itself in pure water?
Well, if you take two iron nails, connect them to a battery and a light bulb, and place them into an acidic water solution, the bulb actually glows. This proves without a doubt that there is a flow of electric current. And what exactly is carrying that current through the liquid? It's those hydrogen ions we talked about earlier separating out in the water. Acids produce these ions in aqueous solutions, and that's exactly what allows electricity to pass right through.
But listen,
We have to be incredibly, incredibly careful when we're mixing these raw chemicals with water. You've probably seen this stark warning sign on containers holding concentrated acids and bases, and there's a good reason for it. The process of dissolving an acid or a base in water is highly exothermic, which is just a fancy way of saying it generates a massive amount of heat.
Which brings me to a super critical safety question for everyone. While you're diluting an acid in the lab, why is it an absolute, non-negotiable rule that the acid should be added slowly to the water and not the water added to the acid? Think critically about that massive heat generation we just mentioned. If you just pour water straight into a concentrated acid, that sudden, intense burst of heat can cause the whole mixture to rapidly boil and splash violently out, causing severe chemical burns, or it could even shatter the glass container right in your hands. So remember, always add acid to water, and do it slowly.
And that brings us to our final topic, Section 5, the power of pH.
We finally reached the ultimate categorization tool for all our chemical substances. Fun fact, the P in pH actually stands for potens, which is German for power, so we're literally measuring the power of hydrogen. It's a scale that runs from 0, which is insanely acidic, all the way up to 14, which is highly alkaline or basic. Right in the middle at 7 is perfectly neutral. If you look at how it's mapped out, notice how as the blue area representing hydrogen ions decreases, the pH number actually gets higher, moving us into basic territory. It's just a brilliant, simple visual tool to measure exactly how strong or weak any solution is.
Let's look at how some everyday items map onto this scale. Lemon juice has an approximate pH of around 2.2, making it quite acidic. Things like pure water and human blood hover right around that neutral 7 to 7.4 mark. If you take an antacid, something like milk of magnesia, you're looking at a basic 10. And a strong industrial chemical like sodium hydroxide, that shoots all the way up to a highly basic 14.
But pH isn't just something confined to a chemistry lab. It dictates literal life on Earth, and even beyond it. Our very own stomachs produce hydrochloric acid at a very specific pH just to digest our food. Look up to the stars and you'll find that the atmosphere of Venus is actually made of thick, swirling clouds of sulfuric acid. And, returning right here to Earth, if our rainfall drops below a pH of 5.6, it officially becomes acid rain. This lowers the overall pH of rivers and lakes, making survival for fish and aquatic life incredibly difficult.
As we wrap up today's lesson, I really want to test your understanding of these concepts. Think about everything we've just learned about mixing acids in water. How exactly is the concentration of hydronium ions affected when a solution of an acid is diluted?
Seriously, think about it. If you increase the overall volume of water, what happens to the amount of ions per unit volume? Ponder that next time you're mixing a drink or cooking in the kitchen. Look at the chemical world just a little bit differently. You've been an absolutely fantastic class today, and with that, class is dismissed. Please follow and subscribe our channel and comment notes to get notes on these topics. Catch you guys next time.